Hello everyone, my name is Alexis Tantet. I've been working at the Institute of Marine and Atmospheric Research in Utrecht in the Netherlands during my PhD, and then did a postdoc in Hamburg University. That's where I've worked on ergodic properties of dynamical systems and stochastic systems, and in particular the spectral properties of transfer operators. This is something I'm going to present today. I am now doing a postdoc at the Laboratoire de Météorologie Dynamique in Paris, or LMD. So why to study the mixing spectrum, or the spectrum of transfer operators? The motivation is basically to study not individual trajectories of dynamical systems, but rather their statistical properties, such as the decay of correlations, resonances, as well as the linear response to forcing, and also global bifurcations or attractor crisis, which is an extreme case where the linear response is not possible. The objective is to be able to tackle high-dimensional systems eventually, such as the climate system, something that Henk Dijkstra will be talking about. So today I'm going to talk about the theory behind these transfer operators, the ergodic theory, while Henk Dijkstra will focus more on applications, such as to the study of weather regimes. So on the right, you see three examples of what we're going to talk about. On the top, there is a correlation function in time, decaying. In the middle, a power spectrum with resonances, strong peaks in frequencies. And last, a bifurcation diagram, not of stationary points, but rather of statistical steady states of chaotic attractors. So let us start with a simple example, the deterministic Hopf bifurcation. The normal form of the Hopf is given by these two equations with a radial direction and an azimuthal direction. Because of the nonlinearity, the system of ordinary differential equation undergoes a bifurcation as the parameter delta here is increased from negative values to positive values. When delta is negative, the system, as it evolves with time, converges to a stationary point. The eigenvalue of the Jacobian, the linearization of this vector field here, have negative real part. The stationary point is stable. As delta increases, the system is still stable, but there is a slowing down of the convergence to the stationary point. Eventually, the eigenvalues of the Jacobian cross the imaginary axis and result in a periodic orbit associated with the imaginary part of this complex pair of eigenvalues. But the stability of this orbit is still relatively weak, so there's a slow convergence to it. As delta is further increased, the convergence is faster. Now, what can we say if we study instead the stochastic version of the Hopf equation, or rather one stochastic version of the Hopf bifurcation? In this case, I've added terms in red with a drift, which is deterministic, and a noise term in the radial direction and the azimuthal direction, which is given by a Wiener process or Brownian motion. These stochastic perturbations are responsible for the very erratic behavior of trajectories in this case. This is the case for delta negative and delta positive. So before and after the deterministic Hopf bifurcation. In red, I represent the stationary distribution, the density of the stationary distribution or invariant measure of the system. I will talk more about it. The more the colors are red, the more the system spends time in this region. However, It never stays too long close to the stationary point. As the parameters increase, we can see the signature of the limit cycle, but the trajectories are always going around the limit cycle. How to better describe this behavior, which is much more complicated here than in a deterministic case? Two approaches have been proposed. One is that of random dynamical systems, which can be seen as a generalization of random dynamical system, extending the space, the state space, to take into account the noise part. We still look at trajectories, but in a broader space. And there's another approach, which is the one I'm going to present today, which is the stochastic analysis of the Markov semigroup, which I will define. In this case, we are not interested in trajectories, but rather on the average behavior of the system. So we average with respect to the noise. Let's give an example of what we call mixing. In the statistical approach, we study the evolution of ensembles rather than trajectories. Ensembles can be thought either as probability densities, if you're familiar with that, or as an ensemble of individual members. Here, each member has an initial condition which is plotted in the plane of the state space. They are marked in red if they start on the left, and blue if they start on the right. To propagate this ensemble, I simply integrate stochastically each of these points forward in time. This is the evolution that is represented here. We can see that there is a first regime of strong contraction towards the remnants of the limit cycle. Later, at a slower rate, there is then diffusion along the limit cycle. The noise is responsible for the mixing of each of the members. Eventually, at the end, or as time passes, each of the members continue to evolve erratically. However, it's hard to distinguish which part is red from the blue. It's rather purple. There has been a mixing of these of the markers marked by the two colors. It is impossible to say now from where a point here came from initially. This is what we call mixing. There's a loss of information. And even though these points still continue to evolve erratically, the ensemble behavior, the probability to find members in a given region of the state space, is no longer evolving. How to formalize this? First, I can give you can find another example of mixing, which is not due to stochasticity, but rather to the chaoticity of a system. An example which is very nice is given by the Lorentz flow. You can click on this link here. I will let you do that on your own. Let's continue with the theory. Let's start with the deterministic case, which is in some ways simpler. We started with the evolution of an ensemble. If we have a set of members, we can define a probability distribution rho 0 as a sum of Dirac measures centered on the initial condition of each member. These are the initial red and blue dots that we saw before. It's the probability distribution integrating to 1. We can then look at averages of observables G, for example, in the climate case, the temperature at a given location, with respect to this probability density. And we get the usual sample mean here. As I evolve each member with the flow, I get a new density where each member with a Dirac measure centered on each of the new members' position at time t, this defines a new probability distribution. The average of the observable G has also evolved and is given by the sample mean of G evaluated at the position of the members evolved with time. That's what I represent in the schematic here. These are members that evolve in time, and the probability distribution, which is represented by the contours here, evolved there. And we use it to calculate averages with respect to of the observable. In fact, there is a duality between integrals of the observable with respect to the propagated density probability distribution rho t of a. This one is equal to the average of the propagated observable with respect to the initial distribution. This propagated density is unique. It defines an operator which is called the transfer operator, while that one defines a dual operator called the Koopman operator in the deterministic case, or the Markov operator in the stochastic literature. In the stochastic case, ordinary differential equations are replaced by stochastic differential equation with a Wiener process here in red. It governs the evolution of stochastic trajectories, which now depend on the realization omega of the noise. Formally, we can define the Koopman operator for some time t as the expectation with respect to the noise of the observable evaluated on the state propagated by the flow. In the deterministic case, we don't need to take the expectation because there is no noise. The transfer operator is then defined by duality, as already mentioned earlier. And this is, so here the function g is represented in blue. The initial density rho is represented in dashed contours with rho 0. As it's propagated by the transfer operator, we get that density, which is equivalent to propagating g. What are the properties of this transfer operator? Due to the flow, due to the group properties of the flow, the transfer operator semigroup, the transfer operators, the family of transfer operators, is a one-parameter semigroup, where the parameter is time. These operators are also linear, which translates in having the operator at time t plus s equal to the application of the operator at time s, and then the application of the operator at time t for positive times. Another property is that of contraction, at least when we consider densities in the space of integrable functions, which means that the norm, so the L1 norm, the integral of the absolute value of the transfer operator applied to the density, is smaller than the original norm of the density. In other words, which means that basically we cannot lose any member. If the density, if the function rho is actually a density, so it's positive, this is an equality. However, if rho has negative values, this can only be an inequality. The conservation of probabilities in the phase space, in the results, in the evolution, the infinitesimal evolution of densities, to be given by the opposite of the divergence of a flux. This flux is given by an advection term in the deterministic case and the stochastic case, plus a diffusion term in red in the stochastic case. This partial differential equation, it's called the Liouville equation in the deterministic case, or the Fokker-Planck equation in the stochastic case. There is a dual equation for the Markov operators, which is called the backward Kolmogorov equation. I want to mention two very important scientists in the ergodic theory, von Koopman on the left, who is also one of the first among the first scientists to use computers for numerical weather predictions, and Birkhoff on the right. The two have proved the two different versions of a major theorem, and there's been actually a controversy on who was the first to prove that result. Let's continue with the theory. For next, we're gonna need to define what an invariant measure is. Loosely speaking, the invariant measure represents the statistical steady state of a stationary system. Its property is that if we apply the flow at any time to a set in the phase space, its measure is invariant in time. It's not the set itself which is invariant, it's the measure of the set. As a result, if we integrate observables evolve with time, either with the Koopman operator or the transfer operator on measure, we have an integral which is equal simply to the integral of the observable with respect to the invariant measure. In other words, those integrals are constant with time. There is another property which is stronger than the invariance, it's the ergodicity of the measure, which states that if a set is invariant, then its measure is either 0 or almost 1. Which means that basically the measure is only aware of one invariant set. It doesn't care about possible other invariant sets. So for example, if we have two attractors, an invariant measure cannot give weight to both one attractor and the other, because those are invariant sets. So either the measure of one is full and the measure of the other is 0, or it's the opposite. In this case, we can apply the ergodic theorem. Birkhoff's version is the latter, that if mu is ergodic and we have an observable G in an integrable space, then the limit of time averages, which is represented here, it's the time average of the observable G, is equal to the measure of G, the integration of G with respect to that measure. So not only this integral is constant with time, but we can use long integrations of our system to compute it. This is true for mu almost every initial condition, which means that it's only true if we start in the invariant set, in the support of the measure. If we start outside of it, we don't know if it's going to be the case. We will see that it has strong implications. A stronger property concerns the correlation function in mixing. So correlation functions can be defined with respect to the measure as such. Between two observables for a time t, it's the integral of the product of one observable by the propagated observable minus the product of their means. I give an example here on the right. The power spectrum is the Fourier transform of this correlation function. It doesn't have to be a smooth and absolutely continuous function. It could be composed of Dirac measures, for example. So the two, it's possible to go from one function to the other. What about mixing and correlations? Mixing is a stronger property of ergodicity. It's defined mathematically for two sets as the limit of the measure of the intersection of these sets, as one gets fixed and one is evolved. If this limit, if the system is mixing, if this limit is that of the measure of the set by the measure of the other set. We can see here that time is no longer here, which means that the sets have forgotten about their initial condition. This is illustrated on the right with the example that we already saw. As I propagate with the transfer operator my probability distribution, the points composing this distribution are eventually mixed. We cannot recognize from where each point came from. This translates, we can go from sets to functions. And this mixing property is equivalent to having the correlation function decaying to 0 with time for any pair of observable in a set of integrable functions. Okay, so we can see already that the decay of correlation and resonances are connected to the transfer operators or their dual. To go further, we would like to get to know more about the actual decay rate of this function. How fast do the correlation decay? Or how strong are resonances in the power spectrum? To do so, we can formally decompose the correlation function on the spectrum of the transfer operators. Because of the semi-group property of the latter, we can decompose the correlation function between any pair of observable at any time t positive as a sum of contributions from exponentials with a rate given by the complex eigenvalue lambda k and weighted by the weights wk, which depend on the scalar product of the observables with the left and right eigenvectors of the transfer operator. Or in other words, of the eigenvector of the transfer operator and the eigenvector of its dual. The lambda k, the eigenvalue of the transfer operator at time t, is actually the exponential lambda kt, while the lambda k is the eigenvalue of the generator giving the family of transfer operators. This stems from the semi-group property and the linearity of the system. Regarding the power spectrum, we have a similar decomposition in terms of Lorentzian profiles. I should say that this is an illustration in the simplest case when the spectrum of the transfer operator is actually discrete. However, because we work on space of functions, the operators act on function, these spaces are infinite dimensional. In general, they could be a continuous part of the spectrum or essential singularities, which will result in additional term in the correlation function in the forms of integrals rather than sum, which may result in a slower decay than exponential. This actually happens in many cases of chaotic systems. But for practical applications, let us focus on a discrete spectrum. We can see that the correlation function will decay only if all the exponentials here are associated with an eigenvalue lambda k, which has a negative real part. How fast the correlation decay will depend on how far the real parts of these eigenvalues are from zero. Regarding the power spectrum, the decomposition allows us to look at resonances. Here is an example of power spectrum with the angular frequency given in this axis, negative, positive. You can see that, and here is the eigenvalues lambda k of the generator in the complex plane. When we have eigenvalues which are close to the imaginary axis, if the weights here are not zero, they will result in peak in the power spectrum or resonances. The closer the eigenvalues to the imaginary axis, that is to say, the smaller the real parts of the eigenvalues, the stronger, the sharper will be the peaks. While the imaginary part of the eigenvalues give the position of the peaks in terms of frequencies. In the extreme case, when the eigenvalues have zero real part, these peaks will be discontinuous. They may be represented by Dirac measures, for example. So the power spectrum is not a density anymore. It's rather a distribution or a measure. In this case, this is associated with the fact that the correlation function is not decaying in time. It has purely oscillatory components. This is related to a theorem that states that if the function is decaying fast enough, the power spectrum, its Fourier transform will be given by a density with decaying with the angular frequency. If it's not the case, if the system is not mixing, we can have non-trivial behavior. Let's continue. How about applications to the stochastic half bifurcation? Okay, so we have the stochastic differential equation here that I'll write down again. The backward Kolmogorov reads this. It is the differential operator, G here, that can be associated with the generator of the Markov semigroup, the dual of the transfer operators. So we have an explicit formula for this operator in this case. To look at this spectrum, it's not possible to analytically solve the equation for these operators. Instead, we're going to use a small noise expansion. That is, we're going to assume that this term here is very small compared to the contraction here. We're going to do that before the bifurcation, the deterministic bifurcation, and after the bifurcation. In this case, we can decompose the eigenvalues 0th order, 1st order in the noise, etc., etc. And we're gonna do a Taylor expansion of the trajectory about the fixed point at 0 and about the limit cycle. I'll go quickly through this computation. When we do so, we can obtain formulas for the spectrum of the differential operator. Before the bifurcation, we get this formula for the eigenvalues. I represent them in the complex plane here. We have a triangular structure where the eigenvalues are spaced from the imaginary axis by a parameter mu, which is actually corresponding to my delta here. Which means that the more stable the fixed point, the further the eigenvalues from the limits from the periodical. The eigenvalue from the imaginary axis. The imaginary part of the eigenvalues are spaced by the angular frequency that corresponds to this number. The eigenvectors are also given by the products of harmonic functions in the azimuthal direction and polynomial in the radial direction. The further the eigenvalues from the imaginary axis, the higher the order of the polynomial in the radial direction, and it's the same for the harmonic in the azimuthal direction. So the further the eigenvalues from the imaginary axis, the stronger the nonlinearities in the eigenvectors. This will have implications later. If we decrease the stability of the limit cycle, of the stationary point, sorry, of the deterministic stationary point, the eigenvalues get closer to the imaginary axis. After the deterministic bifurcation for delta very large, we get a decomposition that has a form of parabola in first and second order. To first order, we have a purely imaginary. We have a set of eigenvalues which have a purely imaginary part for L equals 0. We have a line here, and then we have successive line depending on the stability of the limit cycle. But the addition of noise is responsible for an additional real part, which pushes the eigenvalues further from the imaginary axis. Which means that we have while in the deterministic case we have non-zero, we have eigenvalues with zero real part, which means that we have purely oscillatory components in the correlation function, which prevent it to decay, so that we don't have mixing. In the stochastic case, the noise is able to introduce what we call phase diffusion, which is responsible for pushing the eigenvalues away from the imaginary axis. There is mixing. Okay, so the two phases we saw with first a contraction regime to the imaginary axis and then diffusion along it are represented by the timescale, the rate delta, which defines the stability of the limit cycle. The more stable, the first time we have convergence to it. While the rate of mixing is determined by this term arising through diffusion. The latter depends on the stability of the limit cycle. On the level of the noise, which is quite intuitive, but also on another term, beta. We will come back to the origin of this term. See, it's quite important. Finally, the eigenvectors are again given byproducts of harmonic functions and polynomials. Yet, there is a term beta with a radial component in the harmonic function, which is responsible for the twisting of the isolines of the eigenvectors. These were small noise expansions. To go further, to test the quality of these expansions, so how much we can ignore this term, the higher order term, and to test what happens closer to the bifurcation, we can use numerical applications. The methods to get these spectra numerically will be described further by Henk Dijkstra. It's called Ulam's method. It's basically, the idea is to discretize the transfer operators into transition matrices and to estimate the transition probabilities, the element of these matrices, from time series. Before the bifurcation, I represent here in black crosses the first order expansions that we obtained from the formula. And in black dots, the actual eigenvalues of the matrices. We can see that there are differences between the position of the eigenvalues. The latter, both estimations are close for the eigenvalues close to the imaginary axis, but tend to get further and further from each other. On the right panel of the same figure, I represent power spectra for different observables, x, x squared, and x cubed. If we go all the way after the bifurcation, we have a quite good agreement between the numerical computation and the small noise expansions. They deteriorate as we go further from the imaginary axis. and they are responsible for strong resonances in the power spectrum. These resonances may appear even before the bifurcation because the eigenvalues are here, excited by the noise, even though we wouldn't see any oscillation in the deterministic case. In the middle, we have the case at the bifurcation, where we see non-trivial structure in the eigenvalues, which could not be predicted by the small noise expansions. Let us try to understand better where the twisting and the phase diffusion comes from. Let us simplify our system to add noise only in a radial direction, and let's see what happens. We can decompose the vector field here into, and the right-hand side here, to a deterministic part of the vector field, V0, with the dt here, and a stochastic part, V1, in red. One interesting method that I would like to introduce to you is the study of hypoelliptic operator with the condition on the Lie bracket of Hermann. The idea is basically to know if there exists a stationary distribution which has a density. So has the invariant measure of this system a density, a smooth density? In the deterministic case, we know it's not the case because we have basically, as invariant measure, the limit cycle itself. I kind of rotated the arc. Okay, but our operator, the Markov operator, now has a second order term associated with the diffusion, which may be able to smooth out the dynamics of density. Hermann's condition is basically to see if this vector field or any combination of the Lie brackets of this vector field with the deterministic one is able to span the state space, R2 in this case. If the vector V1 alone is able to span it, the operator G, the generator associated with the differential operator of the Markov, the backward Kolmogorov equation, is elliptic. This would be the case if we would have a noise term here and the dw theta that we had before. Okay, so we would have one noise vector field acting in the radial direction and one acting in the azimuthal direction. Here we have suppressed the azimuthal part. So our operator is not elliptic. It could be, however, hypoelliptic, which would mean that the space spanned by V1 plus another vector field given by the Lie bracket of V0 and V1 would span R2. The Lie bracket, if you want, it's a kind of measure of the commutativity of the vector fields. Or, in other words, whether with the successive application of the flow for a small time, of the flow generated by V1 and then by V0 and then back in time, whether this is able to, what is the resulting vector from this successive application of the flow? I invite you to look more into the theory. We can compute these Lie brackets for this simple system. We find that in differential notation, V0, V1 is given by this formula. We have a radial component, which we already had, nothing new. But we also have an azimuthal component that depends on beta. Here, sigma is actually epsilon. So if beta is non-zero, this term here, we have a hypoelliptic condition, which means that the the invariant measure of the system has a stationary density. There is a smoothing by the noise. Why is this beta term so important? We can see already here that the term is able to increase or decrease the angular velocity of our system, depending on the radius r. To go further, we can look at a bit of geometry, in particular at isochrones. Isochrones are basically the foliation of the stable manifold of the deterministic limit cycle. It is given by this formula. If I start 2 points on the same isochrone, they eventually end up on the limit cycle with the same phase. That's what this equation means. So in the case when beta is 0, the isochrones here are straight. They are exactly in the radial direction. But when beta is non-zero, they are twisted due to the change in angular velocity here. And it is this twisting that is allowing the noise to propagate from the radial direction to the azimuthal direction. This is a result that one can prove that we have. Okay? And this is exactly this propagation of the noise in other direction that the Lie bracket measure. Okay, so this term, by impacting the angular velocity, by giving it a dependence on the radius, is able to twist the isochrones, which is responsible for the noise to propagate from the radial direction to the azimuthal direction. This is what I show here. If we have beta equals 0, the noise is acting only in the radial direction. The Lie bracket V0, V1 can be seen as by propagating for a small time with the deterministic flow, so we rotate. Then we apply the noise vector field for a small time, we go there. Then we come back by the flow, and we come back by the stochastic vector field. We end up in the same direction. However, when beta is non-zero, we apply the flow, the deterministic flow, to have the same result. But applying the noise is making us change isochrone. Coming back, we are still in a different isochrone. So the vector field given by the Lie bracket is not anymore in the same direction as V1. The result is that in the first case, we have a phase which is deterministic. There is no diffusion. We just rotate in the limit cycle. And if I put an ensemble on this limit cycle, they will all rotate with never meeting each other. They rotate at the same speed. If we add noise, now we see phase diffusion appearing. Members start to mix on the limit cycle. This explains why we have, in addition to a noise part in the eigenvalues given by the radial direction, we have the beta term that arises, which is due to the injection of noise in the we have a part which is due to the noise directly injecting in the azimuthal direction, and the part of the noise from the radial direction transmitted by the deterministic flow to the azimuthal direction. So we can have a quite detailed description of the stochastic half bifurcation with these tools. I will go quickly with the discussion. So we can see that the mixing spectrum allows to study correlations and Power spectrum. It brings the powerful framework of stochastic analysis to the study of stochastic bifurcation. The geometry of the system, even though we are in a stochastic system, the geometry of the underlying deterministic system can tell us a lot about how the noise acts on the system. And small noise expansion allow us to compute eigenvalues and eigenvectors of the transfer operators and Markov operators just from the linear stability element of the deterministic limit cycle. More complete formulas are given in the papers. To finish, I would like to mention another type of application, which is no longer the study of stochastic system, but rather of chaotic attractors and of bifurcations of chaotic attractors. Okay, so I give an example here of bifurcation diagram associated with the well-known Lorentz flow, the 1963 model of Lorentz. The Lorentz flow is a reduced version of the Rayleigh-Benard convection on 3 degrees of freedom. It depends on the Rayleigh parameter, which is here the rho. As rho is increased, we have a first bifurcation where the stationary point divides in two. We have a pitchfork bifurcation. The red branch is the stationary point of one of the is the evolution of the stationary point of one of the stationary points, and we have a mirror situation here. As we further increase the Rayleigh coefficient, we get a subcritical half bifurcation. So there is a limit cycle which is unstable that appears here. Okay. As the limit cycle grows in this direction, eventually it will hit on the unstable stationary point at the origin. It leads to a homoclinic orbit. At the homoclinic orbit, here we have a birth, we will see, of a strange set, which is chaotic, but not yet attracting. To have attraction, we need one of the limits. We need the limit cycle here to shrink and to eventually leave the chaotic set. So the chaotic set here has an infinity of periodic orbits, but eventually the one with the simplest period, the one associated with the Hopf bifurcation, will leave, and we get an attractor here, the chaotic attractor from Lorentz. The value of 28 in the original paper of Lorentz would be around here. Okay, so here we have a chaotic attractor crisis. The attractor which is for large value, the chaotic set which is attracting for large value, is actually become unstable here. It's not globally stable anymore. It's no longer an attractor. So it still exists, but there's a bifurcation. Okay? So what happens? A bit of history. To study bifurcations, we saw that in the deterministic case, for low-dimensional bifurcations, or for simple bifurcation involving only stationary points or Hopf bifurcation or limit cycles, we could study either the Jacobian of the stationary point or the Floquet elements of the limit cycle. But for chaotic sets, we don't have all these tools. So what is happening? Why is the attractor no longer attracting? So in blue, I show a trajectory in the three-dimensional space of the Lorentz flow of around the attractor. In black, I show the stable manifold of a limit cycle. The limit cycle which originates from the Hopf bifurcation. So we are in this case here. There's a small limit cycle. There is the attractor. As I decrease rho, trajectories starting from the fixed point, so unstable trajectories, go and eventually they are actually on the stable manifold of the limit cycle. So it arrives exactly on the limit cycle. Okay. This means then of the limit cycle is now at the boundary of the attractor. It has merged with it. And eventually, as we continue, the trajectories from the fixed point now no longer go to the attractor, no longer go to the limit cycle, but they go inside the limit cycle to the stationary point that emerged from the pitchfork bifurcation. This is a description of what happens at the attractor crisis. But can we learn more in terms of statistics? To do that, we computed the transfer operators numerically with the same method. So we integrate many trajectories of the system with a Runge-Kutta-4 scheme. We integrated billions of trajectories for a given duration tau. We discretized the ball containing the attractor and all the interesting elements into many boxes. So we need a supercomputer to do this. These are tests showing the convergence, the numerical convergence with the number of boxes of the leading eigenvalues. So we are basically standing here. So we are pretty close to convergence. Maybe not close enough. Here, I represent the real part of the eigenvalues as the parameter rho is decreased from right to left. We can see that some of them actually converge to the imaginary axis, to 0, at the attractor crisis, and then decreases again. So it means that, basically, the attractor here is able to attract densities quite fast. As it becomes less and less stable, here I talk about global stability of the attractor, the eigenvalues get closer to 0. There is a slowing down of the attraction of densities to the attractor. Eventually, there's a crisis. The attractor is no longer attracting, and it becomes more and more unstable, as is measured by this spectral gap here. Okay, so we can actually see the signature of the loss of global stability of the attractor in the eigenvalues of the transfer operator. And one last message is that a big question in the climate community, for example, is whether this slowing down should be observable from long trajectories invoking ergodicity. In fact, when we consider deterministic chaotic system, dissipative system, which have attractors with 0 volume, long trajectories evolve around the attractor and do not collect any information about what's going on further from the attractor. That is why the standard linear response theory, or fluctuation dissipation theorem, for those who know, is not working. This is associated to the fact that the transfer operators have 2 families of resonances. Transfer operators can act on densities evolving on the attractor, and the eigenvalues associated with this part of the operator is responsible for the mixing on the attractor, on the support of the invariant measure. However, there is also another part of the operator that acts on densities away from the attractor. And the eigenvalues are associated with this part of the operator are not responsible for the mixing on the attractor, but rather from the contraction to the attractor. And actually, the eigenvalues which are affected here by the crisis are the stable eigenvalues, so the ones that are responsible for the contraction to the attractor. If I take a long trajectory to estimate my operators, in other words, if I estimate the part of the operator on the attractor, I will not have access to the eigenvalues responsible for the contraction to the attractor. Which means that I cannot use long trajectories to study the slowing down of the attractor of the system at the approach of the crisis. The usual early warning indicators based on the slowing down of the correlation function will not work. And that's actually what we find in the paper corresponding to this study, is that the correlation functions are not actually decaying faster at the approach of the crisis. That was the last question. So conclusion, the mixing spectrum allows to study, I said it already, the correlations and the resonances in both stochastic case and chaotic cases. Although the numerical analysis is quite challenging, that's what Hank will talk about. Structural change is seen during stochastic bifurcation, which shows that the stochastic analysis approach is complementary to the random dynamical system approach to the study of bifurcation. And the signature of the attractor crisis in the Lorentz system is visible in the stable resonances. So there's quite a body of theory behind it. The difficulty to do analytical work is that one needs to work on spaces no longer of integrable functions, but on distributions taking into account the contraction and expansion property of the system. So you can find more references in the articles. And as I just said, this crisis is not observable just from long-time series. You need to study what's going on away from the attractor. So the stochastic analysis part is not published yet, but is on the archive. There's a finalized version, but it takes time to publish. The work on the transfer operator applied to the study of chaotic system is given by these two articles. One is a study of the Lorentz flow, and the other a study of a chaotic crisis in a big climate model for which we need to use a reduction method to approximate the resonance. Thank you for your attention. If you have questions, I would be happy to reply to them offline.